Welcome everyone. Today in this video we are going to talk about ultraviolet catastrophe. So a very important aspect of blackbody radiation is this ultraviolet catastrophe. So before going into that, I would like to tell you what is blackbody radiation. And after that we will quickly go to ultraviolet catastrophe. So our main point of discussion of this video is ultraviolet catastrophe. But before going directly to that topic, let me briefly explain what blackbody radiation is. In general, if I am talking about blackbody, it is not literally black, right? What is the actual definition of blackbody is that whatever radiation is incident on blackbody, it absorbs all. So if you consider the scale of, let's say, frequency starting from 0, so ideally it is able to absorb radiation of frequencies in the range between 0 to infinity, ideally, means theoretically. Or if you consider the wavelength also 0 to infinity. So whatever wavelength is incident on the blackbody, and from the inherent property of blackbody, the same amount of radiation is reflected back also. So if I am saying that a blackbody is maintained at a constant temperature T, what does it mean? Whatever energy it is absorbing from the environment, the same kind of amount of energy it is radiating. That is why it is able to maintain a constant temperature. So whenever you are given that a body is maintained at a constant temperature, it means it is in thermal equilibrium with the surrounding. Okay, so this is the main concept of blackbody radiation, that whatever incident radiation it has, the same amount of radiation will be emitted. Now practically, in our practical life, if you want to design a blackbody radiation, and it is designed in such a way that if you make a container, okay, and if in this container if you make a very small or tiny hole, and if you incident radiation through that particular hole, then what will happen? Whatever radiation you will give, that incident will be absorbed, completely absorbed inside the blackbody cavity. Let me explain. For visualization purpose, I am showing it a little bigger, but it is very tiny. You can consider like it's like a pinhole. So let's say a light wave is going in this way. So it is entering. So how it will behave? It will hit this wall. Then from it will may reflect. So it will show some random behavior. As you can see, it will go randomly. It will reflect randomly from the walls, and ultimately it will get absorbed. If I show you with the help of, let's say, arrows, the path of this incident radiation, you can see it in this way. So whatever wavelength you are giving, this whole incident will be absorbed inside the blackbody radiation, and inside the blackbody this wave will form standing wave. They are not getting any way. So if I am showing you only any two walls, you see one wall up, one wall below, these walls. So I am taking any two walls. So in between these two walls, there will be forming standing waves. So what is the best example of standing waves? You see, a straight string confined between two resident is an example of standing waves. So similarly, these waves will form standing waves. Okay, and you have to consider 3D generalization because you are considering a 3D structure. So you just consider straight string, one-dimensional standing waves. The same thing you consider for 3D case. Okay, here. So you will get 3-dimensional standing waves formation, and each standing wave will have two nodes at the walls. So if you consider these two walls, let's say you are considering this wall and this wall. So the standing waves will have two nodes, one node at one end, another node at one end. Okay, and there may be various possible modes. Okay, it can be like this, it can be like this, but one thing is sure, that two nodes will be there at the end. Node means where there is no deflection. Okay, if I'm considering let's say the mode like this, what does it mean? This is one node, this is another node, and here you can see this is antinode. Okay, and the distance between two nodes, so one node will be here also. Distance between two nodes is lambda by 2, and distance between an antinode and node is lambda by 4. So what does it mean? the standing waves will have two nodes and the distance between them will be half integral. So, half of a full wavelength lambda by 2. So, n lambda by 2 you can consider in this way. So, this is the basic of this Blackbody radiation. So, this is the standing waves or electromagnetic waves serves are equivalent to the harmonic oscillators. Okay. So, that is why in Blackbody radiation we take the example of, we take the help of harmonic oscillator. We got similarity. So, as in case of harmonic oscillator there are 2 degrees of freedom, and you know from equipartition theorem 1 degree of freedom corresponds to energy kT, sorry half kT. So, 2 degrees of freedom will be kT, 2 into half kT. That is why for each standing wave the energy associated is half kT into 2, that is kT, right, for each standing wave. Now, if I am considering that how many possible standing waves are there if you consider the frequency range between nu to nu plus d nu. So, this gives you basically the number of modes between nu and d nu. If I am denoting them by this g nu, d nu, okay. So, this is given by 8 pi nu square d nu upon CQ. So, this is the nodes, right. Now, what will be the energy per unit volume in this node? Okay. So, this is the number of modes, number of standing waves you can say, and one standing wave is carrying energy kT. So, we can define the energy density u nu, okay, energy per unit volume in this frequency range. So, what will be that? Number of standing waves into the average energy of each standing wave, that is kT. So, this will become 8 pi kT upon CQ nu square d nu, and this we plot in the Blackbody radiation curve. U nu, this is Rayleigh-Jeans law actually, divided by nu, and we get experimentally a Blackbody radiation curve like this. So, it increases in the lower frequency range and it achieves a maximum and then it decreases, okay, at infinity it is supposed to be 0, right. So, if we consider, let us say this amount of range, okay. So, this is basically your visible range in the sense its frequency, in terms of frequency you can consider 414 hertz to let us say 6 into 10^14 hertz. This is a visible range. So, this is the experimental curve we obtained for Blackbody radiation, and as you can see this curve is achieving a maxima and then decreasing. But what you get according to this formula? According to this formula you can see as you keep on increasing nu, this energy density is keep on increasing and if you go to let us say infinity, then as per this formula it should be giving you some curve like this. As per this formula it is going like this. So, this is at the ultraviolet end, this is happening at the ultraviolet end, this is visible, then ultraviolet will come. So, what is happening when your frequency is going towards the ultraviolet end, instead of showing a maxima and decreasing, it is constantly increasing abruptly towards infinity, So, this is a violation of the experimental results. This phenomena is known as ultraviolet catastrophe, and you can see it is happening at the ultraviolet end. So, I hope you have understood this brief discussion on ultraviolet catastrophe. If you have any question regarding this, you can let me know in the comment section. I'll definitely like to help you out. Thank you very much.